So we are moving on to FPGA. And first of all, what is it? It stands for Field Programmable Gate Array. Okay, and basically, what is FPGA? It's a kind of IC, and there are circuitry inside, right? The circuitry inside is decided by the code that you the code that you write determines what's the circuitry inside IC. So that's FPGA in a nutshell. Okay. So how you might ask, okay, so how is an FPGA customized? How can you customize an FPGA? First, as I said, you have to write source code, right? So the way that it's developed or invented is that you can decide what's going on here by your code. And the codes that are used nowadays are, one of them is Verilog that I'm going to teach you. The other one is more advanced, it's VHDL. Okay, so you write your code either using this or that, and you can then, once you write your code, like exactly like when you write a C code or C++ code, Python, MATLAB, then, well, for example, for C++, you compile your program, right? So here it's the same thing. You synthesize your logic circuit with a code. So you first write source code. These are the steps to customize your FPGA. So you write your source code. And as I said, the languages can be that you can use. One of them is Verilog, the other one is VHDL, which are basically the same thing. Once you know this, going to VHDL is easy. So once you write your source code, then the analogy will be compiled. So you have to synthesize with a software your circuit, right? And then the output file will be downloaded to FPGA. File will be downloaded to FPGA. Sorry, FPGA. FPGA IC. Then that's it. Okay. So after going into what's going on inside this IC that I said is basically FPGA, I'll show you how to write Verilog, which is basically C-based. It's very similar to C. The other thing I want to talk about before moving forward is that the confusion between FPGA and microcontrollers. For example, Arduino that you have seen before. The thing is that FPGAs are not microcontrollers. So FPGAs are not microcontrollers. Why? You might ask, okay, but what are the differences? First of all, as I said, FPGAs are flexible, right? Why they're flexible? Because for each code that you write, the IC will do one thing, right? So depends on it's very flexible. Whatever you code it with, it will do it for you. But microcontrollers, they are application specific integrated circuits or ASICs, right? So microcontrollers are ASICs. What does it mean? Application specific integrated circuits, meaning that they are built to do a specific task. And that's it. They're not flexible. So that's one of the important differences between FPGA and microcontroller. But the thing is that FPGAs, they can act like microcontrollers. So microcontrollers are ASIC, not FPGA. Okay. Microcontrollers are ASICs, but if you can design your FPGA to act like one of the microcontrollers. So it's like a higher level. And another thing is that they don't execute code like microcontrollers. So that's another difference. The major one is that FPGAs are are flexible. Microcontrollers are the way that they built to do something, and that's it. When you buy it, that's it. So they are ASICs. Okay. So you might ask, why should I learn about FPGAs? What are applications of FPGA? If you just now go and Google FPGA applications, and millions of applications will come up, like automotive, medical, aerospace, they are everywhere. So it's a very important subject to learn nowadays. It's interesting that 90% of FPGA boards that you buy, they are, so around 90% of them, they are supplied by this company, Xilinx. Why? Because they are inventor of FPGA. So again, if you Google Xilinx or FPGA board or the software, this is the first thing that will come up. 90% of the stuff out there are from Xilinx. And Xilinx has a competitor that they are competing for a long time. It's called Altera. So Altera, after Xilinx, started to create FPGAs and work on FPGAs. But now Altera, Intel bought it in 2015. So that's why the software we are using is from Intel, actually. So 90% of, actually 90% are both Intel and Xilinx. But Xilinx was the inventor of FPGA. Okay. But 90% of the stuff on the internet when you Google are from Xilinx and Intel. Because of Altera, Intel now has FPGA. And because they bought basically Altera. And the software we are going to use, Quartus, is actually from Intel. And it's pretty cool. Like if you go to Intel website, it has, and both Intel and Xilinx, they have lots of tutorials, lots of labs to introduce you to FPGA concept. The rest of 10%, they are just, there are other markets that they are working on FPGA. For example, Lattice, Microsemi, and other companies. But mostly it's Xilinx and Intel because 90% is a big number. And we are working in this class with Intel, okay? So now, so far, you know, at least, okay, so FPGAs, and I see that I can program, and it's not a microcontroller, although it might look like one, but it's not. Because it's flexible, it's programmable, the circuit inside will change depending on the code that I write. Now, you might ask, what is inside FPGA? What is inside FPGA? Now, first, there are some major parts inside FPGA that I'm going to talk about. One of them is logic box. and then I talk about them. The other one, interconnects, and input-output block. And I'll talk about all of them. The other one is memory and clock manager. Okay, so first one that I talked about was logic block, not box, sorry, logic block. Anyway, so I'm going to start with logic block. What is a logic block? It contains the logic elements that basically implements your design. Also known as configurable logic block, or CLB. You see CLB a lot. So the logic elements are inside, and it contains logic block by itself contains logic cells. Logic cell. Now, logic cell is basically a small group of basic logic elements. Okay, so if I, for example, Google for you logic cell and go to images, you see, I think I like this one. I bring it to the window that you can see. So when you Google logic cell, this will come up. And you look at the blocks and you might wonder what is LUT, what is FA, and I'm sure you know, like D flip-flop. D flip-flop, FA stands for full adder, and LUT stands for lookup table, three lookup table, three input lookup table, three inputs lookup table. So this is what is inside, basically the simple form of logic cell. And but of course there are maybe more full adder or flip-flops. This is just a simplified version of a logic cell. Okay, now let's start from the left side. What is a lookup table? Lookup table is basically the truth table, which is implemented by hardware. Okay, so it's a hardware implementation of the table, truth table that you already know, and it's like so the way it works, you can program, for example, in digital class, you say, okay, I have 00011011, for example, for two inputs, right? And if you remember, we would say, okay, I have this output, and this corresponds to a specific logic, right? And if I change the output to same inputs, another output, then if I have 1010, then that corresponds to another logic. So this idea of truth table are converted to FPGA as lookup table, or LU. So although in the name of FPGA you see field programmable gate array, actually you don't have you don't see one gate or two. You don't see gates. You see lookup table, you see full adder, and you see flip-flops, which they consist of gates. Now, for this lookup table, that's what I showed you. Where was it? Okay, this one. So you have two lookup tables depending on the input, three input. It has three inputs, and you can program it. So for example, for 0, 0, 0, it gives you one output. For 0, 0, 1, it gives you another output. So you can program them. And by doing that, that means you're creating different logic gates. So that's fixed in your logic cell. You have lookup tables. Then you have full adder. Why? Why you have full adder? Because going back to lookup table, yeah, I think I told you everything. It's just, it works by bits, lookup tables, okay? And they can implement any arbitrary free input, basically three inputs, binary function. So it's a binary level focus. So I'm done with that. Now I go to full adder. Oh, why there is a mux here? These are multiplexers, right? Why I have a mux here? Because you can decide if the output you want them to go to full adder or you want them to come out. So that's why this is here. Then you have a full adder. Full adder because it's the building block for arithmetic, right? So for example, you can make a subtractor out of full adder. You can, so it's like a building block. That's why you have a full adder there. Then you have another mux here. Again, you can decide if you want to use full adder or you just want to pass it. So that's why you have one mux here, one mux here, multiplexer. And then DFF, I'm sure you know that it's basically flip-flops, and which is a basic building block for when you need sequential circuits or system. So in other words, any systems that has a notion of time is called sequential circuit. That's why you have clocks here, right? So they're controlled by time. So you have one flip-flop or more flip-flops here. And again, the mux here is used to either pass the output or use it. And either go to mux or go to the flip-flop, okay? So as you see, it's pretty cool because you have everything here. You have a unit cell. It's like that has, the unit cell basically can enable FPGA to create logic. You have like a hardware implementation of truth table. So you have that. You have arithmetic and you have sequential. So you have all of them in one cell. And the building blocks, they are created out of these logic cells. Okay. So for example, if I show you this picture, all these, so these are logic blocks, these gray ones, and they are created from cells, logic cells themselves. Okay. Then the other thing is, where am I? Okay. So I talked about logic block, not box, logic block, then interconnects. So now let's talk about how can these logic blocks and cells, how can they connect to each other? That's where interconnects come. Again, you have these interconnects, which is basically more than this. This is a very simplified picture. These are interconnects that are basically connecting cells with multiple logic blocks, okay? How they are made, they're basically interconnects. You can program, because it's all about programming, right? You are programming an IC. So you can decide if you want the connection go from here to here, or to here to here, or here to here. It's all in your code. But all of these routes are available. All of them are available, and there are big numbers of routes in different directions. And then you can decide by coding that which way you want to go to eventually create your logic circuit, okay? And that's why they are basically implemented, they implement the interconnects by switches. So if the switch is on, that means the route is open, and then you can go to another logic cell. So they're controlled by number of semiconductor switches, the routes. Now, so this is a simplified picture. If you look at, for example, your routes, you say, okay, so here there is a switch, for example, okay? But if you look at your switch, you will see by itself, it consists of at least, for example, 6 switches itself that can give you routes, options to go to different directions. There are enormous number of interconnects available for FPGA. That's the power of FPGA, because you can control which cell is connected to which cell, and because there are enormous number of interconnects available, another name that they use for it, they say interconnect fabrics. Because it actually looks like a fabric. There are lots of enormous number of routes available. Okay. Now, that's interconnects. What about input-output block? Any questions so far? Is it clear? Yeah, good. Okay. Now, the third one is input-output block. What is input-output block? Well, it's important to why we need this block, input-output block. Because integrated circuits, they, as you know, ICs, they work with low power, low voltage, and current internally, right? So outside, you might work with high power. So input-output blocks basically contains drivers and receivers to convert the power level for protection. So input-output block are basically input block and output block of your IC that control the level of power. That's why they are there. Because IC by itself, it works with low power. So you need a way to control the power that's going in and going out, the voltage that comes in, comes out, current. That's where you have input-output block. And then the next part that I want to talk about is clock management. That is important part. So for FPGAs, you always need external, almost like always you need external oscillators, because, and then they are used for For example, you have an input frequency and you want to either scale it up or down. So the way to do that, you have some clock management blocks. For example, if you, I don't know if you have heard about PLL or FLL, these blocks are used to boost up frequency. So for this one, or if you want to rescale it, you can use rescalers. So that's another part of FPGA. Another one, the last one that I want to talk about are memory blocks. Memory blocks always included, so you have RAM and you have ROM. Then goes to FPGA. So as you know, most digital systems, they have ROM and RAM, and they are general purpose, and for this, they should be segmented. Now, the last thing that I didn't put in the list, they are hard IP cores that are part of FPGA. What do I mean by IP? Intellectual property cores. And what are they? Intellectual property cores are functional blocks that are available for use in library or hardware blocks. For example, when you connect your board, you need um, a board to, you need a library or hardware block to control HDMI output or USB. So HDMI controller is an example of IP cores or USB controllers, and so on. Okay. So in summary, I introduce you to FPGA. It stands for Field Programmable Gate Arrays. And I said it's an IC that you can control what's happening inside, the connections, the gates that are connected together with a code. And the code we are going to learn today is Verilog, or Introduction to Verilog. And based on that, you'll have an output. Okay. And it's all because the cells that are inside and the interconnects that are programmable, and you can control them.